everybody. In this video, I'm going to go ahead and show you how to approximate the square root of 2 with a Taylor polynomial. We'll be doing three things: finding the Taylor polynomial of degree 3 centered at 1 of the function the square root of x. We're going to use that answer to compute the value at 2 of that Taylor polynomial. And then we want to find an upper bound of the error if the Taylor polynomial of order 3 is centered at 1 and it's used to estimate the value when x is equal to 2 for that function. To begin this process, let's recall what the Taylor polynomial formula is. Okay, so if this is t sub n from this problem, I'm just going to use p for polynomial rather than t for Taylor polynomial. So p sub 3 is going to represent degree 3 because that's what I'm looking for. And to begin this process, we can see that this formula requires lots of derivatives. We'll be evaluating those derivatives, and all of those values, those coefficient values, then will be divided by n factorials. So for whatever a value it is. So that's what we need to first calculate, is a bunch of scratch work first before we can get this answer. So to begin, I'm going to go ahead and write down the function. So I'm looking at the square root of x. So putting this in exponential notation will help with derivatives. The first derivative, if you drop the power down, decrease it by 1. Second derivative, third derivative, and then that's all we need because we just need degree 3. So at this moment, for part A, that's as far as we need to go, is degree 3. The next thing that we're going to need to do for this Taylor polynomial is now evaluate each of these derivatives and function value at whatever your A value is. So A is what we're centered at. So we're centering it at 1. So we're going to substitute 1 into f of x. So the square root of 1 is 1. I would substitute 1 into this function, and again, since it's the square root of 1, all the time, no matter what, if it's in the denominator, so the square root of 1 is always going to be 1. So 1 divided by 1 is still 1. So this is an easier calculation than maybe another example that you might be working with. So right now it's just going to be negative 1/4 and then 3/8. So we've done that next part, so what's left to do? The next thing is to observe in the Taylor polynomial, each of these coefficients is being divided by some type of factorial. So the first one is 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on and so forth until you get to whatever the degree of the polynomial that you were desiring. So for example, for us, we wanted degree 3, so we'll go as far as degree 3. So what I like to do is draw another column and do this calculation. So I'm going to divide this first term by 0 factorial, which is 1. Then the next one is also going to be 1 factorial, then 2 factorial, then 3 factorial. So how did we get 6 from 3 factorial? Well, 3 factorial is 3 times 2 times 1. So I write this down because I need, on a test day, if I don't get a flashcard or any formulas, I need to come up with some way that I'm going to remember how to write this formula down. So I'm going to do all the derivatives. I'm going to evaluate those derivatives. I'm going to now divide each of these numbers by whatever the factorial is. So 0 factorial, 1 factorial, 2 factorial, 3 factorial. And then I'm going to get my new fraction or coefficient that's going to be in front of the next part. So the next part is to observe, okay, so what do I do with these fractions here? Well, except for the 1 is not a fraction, but what do I do with these coefficients? What am I going to do with them? I'm going to eventually multiply them by powers of x minus a. So we've got x, technically this is x minus a to the 0 power, right? Anything to the 0 power would be 1, so that's why you don't see anything here. And then we've got the first one will be multiplied by x minus 1, so your first derivative's x minus a, or x minus 1 in this case since it's centered at 1. And then x minus 1 quantity squared, and then x minus 1 to the third power. And all you have to do now to get the final answer is multiply these straight across. Boom, 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 and those are going to be your answers. So we're adding, of course, each of these rows 1 by 1, and then multiply straight across, multiply straight across, multiply straight across, and congratulations, you've got your Taylor polynomial, and hopefully if you do that quickly, it should have been done in about less than 2 minutes, maybe 3 minutes. It depends on what type of function that you're taking the derivative of. So that would probably be the only place that's slow. And then evaluating the function. So we lucked out because the square root of 1 was just 1. But hopefully you get a scientific calculator if you run into any issues. Decimals would be good to help you get a nice fractional answer. But this is how I organized my answer to get this polynomial. And now let's use it to answer part B. We wanted to compute the Taylor polynomial at x equal to 2. So, and round our final answer. So all you have to do is grab a calculator, and we're going to go ahead and type this into our scientific calculator. Again, I'm a huge fan of Desmos because it's right there, especially in this online world we're living in right now. It's very easy to use. And there's this wonderful button over here that's going to help me convert it to a fraction if it exists, if a decimal form converts to fraction. And so that's what I'm going to use as my final answer, would be to write down both of them, probably wanting to keep a fractional answer as my answer. So let's go ahead and talk about part C. Part C is going to be the longer one. Okay, but if you do a couple of these, it won't be long. So maybe just the first time it might be long, and then once you get in the hang of it, it'll be shorter. We want to find the upper bound of the error if the Taylor polynomial of order 3 centered at 1 is used to estimate the value of f of x is equal to the square root of x when x is equal to 2. So remember, that was what we were originally approximating. This upper bound of the error of the Taylor polynomial is also called the remainder of order n for this Taylor polynomial. And then from this, there was the remainder estimation theorem. So in order for us to find this upper bound, we essentially want to find some value that will bound this remainder. So how do we do that? Where do we start? So just looking at the formulas, I see that I'm going to need a derivative that's higher than what I'm looking at. I see my a is still the same thing that I'm centered at. So I was centered at 1 originally for parts A and B. And I want to find this error when x is equal to 2. So the n here, remember, that's going to also be your degree. So we were looking at a degree 3 or order 3, right? Order 3. So I'm just going to write these down so it's a little bit easier to keep track of. And the next thing that I need to do to determine this upper bound is I need to proceed with figuring this inequality out. So I need to calculate the maximum error eventually. And if I substitute my other values in here, I can see it's n plus 1. So 3 plus 1 would be 4. 3 plus 1 is 4. And then a is equal to 1, right? Of the original problem, it was centered at 1. So I'm just trying to fill in as much as possible that I know so that it's a little bit easier to simplify in the end. So let's go ahead and start to proceed to calculating this maximum. So this maximum of order 4 is going to be by looking at the fourth derivative of the function, and we're investigating it on our interval. So we started at center 1 and we want to go out to x is equal to 2. So what is the maximum value of the function from 1 to 2? A few things I can do to answer that question. First, let me actually take a look at what the fourth derivative is. So in part A, if you look up at part A, you remember that table, how we were going derivative, derivative, derivative. You can add one more entry right down there and take your fourth derivative, okay? So we just drop down the power, decrease the power by 1. So here's our fourth derivative. If we substitute it back into this maximum function here, it's just that maximum value of the absolute value of this function. So we're just looking at and asking ourselves, what is a maximum, or where does the maximum occur of the function 15/16 x to the negative 7/2 power? Well, one way we can do that is by looking at the first derivative test and determine if at the critical points there's a change in signs, if it's going from increasing or so going from from increasing to decreasing would produce a maximum point. So one quick way without a graphing calculator to look at the graph would be to look at your first derivative test back from calculus 1. And if you take a look at this function here, and if you did look at the graph, or if you know about your parent functions in math, right? So x to the negative 9 halves, well, the half part tells you it's a square root, it's in the denominator, and then x to the 9th would be the power you're looking at. If you look at a graph eventually and pull this up, it just kind of looks like a decreasing exponential function. So we actually don't have any critical points. The function is approaching an asymptote at y is equal to 0, which means the first derivative test would conclude that there is no maximum. So we're good there. So there's no maximum on that, which means we need to find then just what is the maximum of the interval from 1 to 2. So looking at this, the original function, which is right here. So if we're looking at the derivative function, if we look at the derivative at x equal to 1 and derivative at x equal to 2, then we can compare and see which one is larger. And I want to clarify here, I don't know if I remember saying it, but remember I said that one way to determine if there was a maximum is using the first derivative test. So that means that we would need to take the derivative of this function. So if you were wondering where that function was, we took the derivative of this function to determine that. So going back to paying attention to your notation, going back to, since I declared that there is no maximum by the first derivative test, I'm going to come back up to this right here. I want to know what is the maximum from 1 to 2. So calculating the two values, so substituting 1 and 2 into this function here, into the fourth derivative, you're going to get 0.9375 for x equal to 1 and 0.0829 for x equal to 2. So clearly 0.9375 is bigger than 0.0829, which means we can choose that value to be the bound for this formula. We can choose that as the maximum that occurs on this interval here. So I'm going to always use fractional form. That's the most exact form. I want to prevent any other human errors, so I don't want to use the rounded answer. So bringing 15/16 back into this formula here, all you are left to do is to grab your calculator, or if, of course, everybody can simplify this, so you can simplify it by hand, or if you are able to use a scientific calculator, type it into your scientific calculator quickly to get your final answer. And yes, if I was doing this by hand, of course, I know what 2 minus 1 is, right? It's 1. 1 to the fourth power is still 1. So it's very easy to simplify by hand. I just want to continue to show you how easy it is to use Desmo's scientific calculator for this. So as a mathematician, we usually like to use the most exact form. So the final answer here would be 5/128 would be our upper bound error for this Taylor polynomial. And that's all we're going to do for this problem. Have a great day.